Hey, it's Michael. Hey, now that you've got a working MicroBlaze running your Hello World application, what's next? How do you get your MicroBlaze microcontroller to do useful work to control your external hardware? I find the easiest way is to implement the control status registers in your design as advanced peripheral bus slaves. And to communicate with them, I add an APB, an AXI APB bridge to the block design, as shown here. The APB bridge can support up to 16 slaves, making it very easy to have multiple sets of control and status registers, each with their own advanced peripheral bus interface. Let me go ahead and export this interface. I'm just going to rename it. Get rid of that pesky underscore. All right. And I'll save that. Let me go ahead and assign the base address to that new interface. So I'm going to go ahead and assign all. I'll see that APB M0 has a base address of whatever this is. By the way, feel free to edit this once you're more familiar with block design and the address editor. Doesn't have to be this, but doesn't hurt either. All right. So back to our diagram. Let's have a look at what we've just added to our block design. Moving over to the sources, I can right click on the block design and I can create HDL wrapper. Go ahead and let Vivado manage that. And once that's been created, I can double click and there it is. That's what an advanced peripheral bus looks like. Now there's a wealth of information on APB online, including information directly from AMBA, Advanced Microcontroller Bus Architecture. So if you need to know more, it's all there. Let me just quickly walk you through the signals that are used in the APB3 implementation in Xilinx Vivado. We have P clock. Everything is synchronized to P clock. You have a select line, one for each slave. In the case of Vivado, there's an entire bus associated with each slave interface, including P select. P enable is asserted during the data transfer portion of the bus cycle, where P select is asserted during the entire bus cycle. P write is high for write access and low for read access. P address is the address of the write or read transaction. P write data, PW data, is the data that is written during the transaction. PR data is the data that's driven by the slave back to the master during a read access. Then we have P ready. A slave asserts P ready to say that it's it's either latched the write data or driven the read data back to the master during the transaction. We have P slave error. I have not used this signal. I just drive it 0, but I'm sure it could be used to indicate that the master is accessing undecoded address space or an illegal address, that sort of thing. The remaining signals are part of the spec, but since I'm looking at the latest version, which includes version 5, so a lot of stuff in there that isn't needed for the simple accesses to control and status registers that I'm going to demonstrate. All right, so at the top level where I've instantiated this wrapper, here are the APB ports in the top level. The other ports are quite simple. I've got a clock going into the block design. I've got a reset going into the block design. And then we have our AXI UART, transmit and receive, go to the outside world. And here I've written a small advanced peripheral bus slave interface that encapsulates the control and status registers needed for this design. Let's have a look inside of that. So my APB slave interface receives the same reset and clock signals that go into the block design and ultimately clock the MicroBlaze microcontroller and the interconnect logic and so forth. There's the APB bus, and here are my control and status register ports. So how do I interface to the APB? Well, the read side is very simple. It's simply a combinatorial function of the address. Based on the address, the read data bus is driven with the selected register. I have 4 status registers, I have 4 control registers, and I have a simple version register that returns a static value that I've set up in the top level of the design. By default, I return a value that's fairly easily human readable that indicates that you've tried to read an address that is not used in the design. So that's the read logic, just a straight decode of the address. On the right side, we use the positive edge of the clock and the active low reset. The reset, which is typically only asserted at power on, in this case, initializes the 4 control registers to a value of 0. When reset's not asserted, if APB select, enable, and write are all high, then the write data is captured into the register selected by APB address. So address 8 is control 0, 9, 10, 11, control 3. Right? I have some miscellaneous logic here that we can disregard for now. But let's pop back out to the top level. This is very important. Since the control and status registers are 32 bits wide, and the address from the MicroBlaze is a byte address, we don't use address 0 or 1. We start at address 2. So we only read long words or write long words. This is a common mistake to start at bit 0 to whatever. So you want to start at bit 2 when your control and status registers are only 32-bit accessible, long word accessible. Okay, so I'm going to go ahead and move up to the control registers here. I've taken a very simple example using the Digilent Arty S7-25 board, which has some LEDs on it that can be easily controlled. It has two RGB LEDs and it has four green LEDs. And what I'm going to do is use my control registers to drive directly the RGB LEDs. I'm using control register 1 for the first RGB LED and control register 2 for the second. And then for the green LEDs, of which there are 4, I'm going to go ahead and drive those with some custom logic. So I've written a little module called LED blink frequency that has an input that sets the blink frequency in hertz. So a value of 0 would be off, value of 1, the LED would blink at 1 hertz, value of 2, 2 hertz, and so forth. And then another little bit of custom logic that drives an LED with a pulse width modulated signal with an 8-bit control in the duty cycle. So when the duty cycle is 0, the output is 0. When the duty cycle is set to all ones, the output remains high. And in between 0 and all ones, the duty cycle varies from 0 to 100%. So the brightness of the LED would be a function of the duty cycle. When it's 0, the LED is off. When it's 1, the LED's, or when it's all ones, the LED is fully on. And as I go from 0 to all ones, in this case FF or 255 for an 8-bit control value, the LEDs will gradually get brighter and brighter. Simple example using the control registers that I've encapsulated in the slave here. All right, let's go ahead and kick off the build. But before I do so, I'll change this version to today's date, 2024, June 22nd, first build of the day. And this comes in handy just to make sure that when I'm running the design in Vitis that I actually have the bit file that was built today and not some bit file that was left over somewhere that's coming out of the configuration SPI and so forth. So I've modified that. I'll go ahead and start generate bitstream. And while we're doing that, let's look at a more complicated example. So here I have a top level module that instantiates 5 APB slaves. I have 5 APB slaves because I've encapsulated all the control and status registers associated with a given external peripheral in each slave. So I have an amplifier board, I have 3 identical synthesizer boards, and I also have the board that that's actually running the MicroBlaze code that the FPGA itself resides on. I have, in this case, I have an SDRAM on the board, so because it's running a bigger application. So what does that look like? I've instantiated 5 APB buses, or I've set up the interconnect signals for those. My block design, which encapsulates all the complex stuff, the MicroBlaze, all the AXI interconnect, the SDRAM controller, the UART, the local memory, and so forth. is wrapped inside this wrapper. And I have the 5 APB master ports, which I then connect to my slaves. In this case, the first slave is a simple set of control and status registers that operate on the logic of the board that the FPGA sits on. Not much going on there. You can recognize the version I showed you in the earlier design. User access state is interesting. Let's go have a look at what that is. There's a user access primitive available as part of the Xilinx library, the Vivado library, that outputs a 32-bit value into which a timestamp is embedded. And that timestamp can be decoded and displayed, for example. And it tells you the date and time that the bit file was generated by Vivado. I use that. Well, it's free, it's easy to use, and I use it all the time just as a sanity check that I'm running the bit file I think I'm running. All right, I've got a APB slave for each of my 3 synthesizer controllers. Let's take a peek inside them. I have the ports for the APB slave device, and then I have the ports that are unique to that particular synthesizer. Inside of this module, I've encapsulated an APB slave interface with the control and status registers that are used to control the various bits of logic needed by the synthesizer. I have a little master interface for a PLL chip, and I have another master interface for an attenuator chip, and so forth. Fairly simple, but it by making use of this hierarchy, I can, one, keep all the logic hidden and not mess up or make the top level module more complex than it needs to be. And I can also instantiate 3 of these because I have 3 synthesizers I need to control. So I don't need to write a separate one for each synthesizer. I instantiate 3 identical modules connected to 3 separate APB buses. And I've simplified the amount of work I need to do. I have another interface or wrapper for the amplifier. Within that, I have a set of, in fact, I use the same APB slave module as I use for the synthesizer here. So I have a set of control and status registers needed for its peripherals. One of those peripherals is a DAC with a SPI-like interface. Another is a same attenuator chip, and I also have a SPI master for an analog to digital converter chip that resides on the amplifier. So all of this complexity is wrapped up inside of this amplifier controller module, keeping the top level fairly clean. So the top level consists of the instantiation of 5 APB slave devices. All right, let's see how our compile is going. Oh, it's done. I'm going to go ahead and cancel that. I'll go File, Export, Export Hardware, include bitstream, and next. Oh, all right, blew that. And I'm going to drop that XSA file into the Vitis folder of this project. And done. All right, so from here, the project moves into Vitis, and I'll do that in a separate tutorial. Have a good day.